Hi. So far we only used bit patterns for representing unsigned integers, and then we were building this adder, and with some mathematical background we saw that we easily can use this adder for extending it with a few modifications to a subtractor. And with this mathematical background that we got from this exercise, we easily now can also use the bit patterns for representing signed integers using the so-called 2's complement. Before I go a bit more into the details of this 2's complement and how we then can use circuitverse for realizing these details in some actual logic circuit, let me just tell you for completeness that there are more ways, more than just one, to represent signed integers with bit patterns. And two other possibilities are also supported by the C language. So we at least should know about them in theory. They are actually, as I know, not actually used nowadays anymore in computers, but they're used to be computers that use these representations. I will not tell you all the details of them, but at least the basic ideas. If we would use this sign and magnitude interpretation of a bit pattern, then a bit pattern with 4 bits, for example, would be identified with a signed integer as follows. We would use this bit here as the sign. Let me introduce a new definition. This sign of A3 is defined as 1 if A3 is 0 and otherwise is -1. So this A3 gets used as the sign, and the remaining bits are used as the magnitude or the absolute value. So here we reuse the definition of the unsigned interpretation. So A2, A1, A0 are used as this non-negative absolute value. Now, what would be the drawback? The 0 can be either represented with only zeros, because then we have the sign of 1 times the absolute value of 0, but also the bit pattern with a most significant bit of 1 and all other bits equal to 0 would represent the 0. You can think of that as -0, and so we have this drawback that 2-bit patterns are representing the 0. We don't have uniqueness. Let me first introduce this notation. If I put a bar above a bit, it means that I'm inverting it or computing its complement. So A here is a bit 0 or 1. Then the definition for the 1's complement, how we would interpret a 4-bit pattern as a signed integer, would be as follows. If the most significant bit is 0, we again interpret it with just an unsigned value as before. So again, we use the same bit for indicating whether we have a non-negative or non-positive value. Now if A3 is 1, we interpret it as minus the unsigned value of A3 and its complement, A2 and its complement, and so on. So that would mean the bit pattern, let's say 0, 1, 0, 1, would have the signed value equal to the unsigned value of this bit pattern, which would be 5. And the advantage of this 1's complement is that we easily now can find the bit pattern of -5. So that would mean -5 is just the interpretation of this bit pattern using the complements of all the bits. And the disadvantage would be that again we have 2 ways to identify a bit pattern with the 0. For example, 0 would be the signed interpretation of 0, 0, 0, 0, and also the signed interpretation of 1, 1, 1, 1. So again, we don't have this uniqueness. The advantage of this 2's complement will be that we, for example, just have one way to represent the 0. We have uniqueness of the 0, and that we can reuse the hardware that we already built, the adder. So it's cheaper to use the 2's complement. And the reason why we can reuse the 2's complement is that our adder is working in this finite cyclic group. And there we saw that, for example, the operation 1 circle plus 15, that's what our adder is carrying out, gives us a 0, which means that this 15 has the mathematical property to be the inverse element of 1. And because of this uniqueness of an inverse element in a group, we know that the inverse element of 1 is 15. So that means we just could identify this bit pattern that we so far identified with a 15 also as a -1. Just give it a different name. And basically that's already the definition that we now say 1 prime is now called the -1. And then of course we also see that this 14 is the inverse element for 2. So we could identify this with -2. And then we could go on like that, but probably we don't want to end up that we use all the bit patterns for negative values. We want to have ideally as many positive values as we have negative values, but that's not possible. You see, if I continue like that, then I have to make a choice here. Should I use this bit pattern to represent the 8 or the -8? Now we want to have simple rules to see from a bit pattern whether it's in this 2's complement a negative value or a non-negative value. And of course we will just use the idea that this most significant bit has the property to show us the sign of the value. So it would be a better idea to use this interpretation with the -8 compared to use the interpretation as an 8. So we have in this case more negative values than we have positive values, but a simpler rule to identify the sign of a value. Let me clear this. So all the other bit patterns we interpret with unsigned values as before. So we also get here 2, 3, 4, 5, 6 and so on. But now you see in red the interpretation as a signed integer and in blue as unsigned integer. But our hardware still would do the same thing. And the hardware doesn't care about how we see things, what kind of meaning we see in the bit pattern. If we feed our adder with this bit pattern and this bit pattern, it would produce this bit pattern. And we could interpret this as this computation here, where we have an overflow, but we would interpret this as adding 1 and 15 and getting a result of 0. Or we could interpret the computation as 1 circle plus -1 and interpret the result as 0, where we don't have an overflow. So detecting whether we would have an overflow in the signed interpretation or not is the next topic. And for the intuitive interpretation, we can use this line here. If we cross it from above or below, it indicates an overflow. Now for this rule indicating the overflow by either crossing the line from above or below, we have to agree on the direction in which we do the counting. And the rule would be, if I, for example, 7 circle plus 2, the counting would be counterclockwise. And if I would have some negative value that I add to something, then I would do it clockwise. Let me show you this in these two cases. In this case, I would start here and do the counting in this direction. I would end up here. Then I cross the line from above. I would get here a -7. And otherwise, I would have done the counting in the opposite direction. I would have started at -7 and would end up at 7. In both cases, I crossed the line. Now, of course, our hardware actually would in this case not count clockwise. it would count counterclockwise by 14, but still we somehow could realize this. Now, before I actually show you how we can do this indication of an overflow for signed integer actually in hardware, let me show you how we can formalize this interpretation, how we can describe the mapping of a bit pattern to these red values. Now you see, if the most significant bit is 0, we basically don't have to do something different from before. So we also can distinguish these two cases, whether the leading digit, the most significant bit, is 0 or not. And if it's 1, then we actually start here counting at -a, and we do the counting with this remaining bits. So we count here from -8 to -1. So the formal definition in this case would be the signed interpretation of this 4 digits is either the unsigned value of A3, A2, A1, A0 as before, if this most significant bit is 0. And of course that means we just could skip this bit here because it's anyway 0. Let's denote that here. Now, if the most significant bit is 1, the signed value that we associate with this bit pattern would be -8 or -2 exponent 3 plus the unsigned value of the remaining bits of the interpretation of the remaining bit pattern. So like that. And of course we could swap here the arguments. From that you also see the range, the general form of the range that we can represent of unsigned integers. It's from -2 exponent 3 to 2 exponent 3 minus 1, from -8 to 7. Now, how can we generalize this to n bits? Then we have a bit pattern where the highest index would be n minus 1, the next index would be n minus 2, and so on. Then we would have in the least significant bit the index 0, and the value would be the unsigned interpretation of the bit pattern, where we only have these bits with index n minus 2 down to a0, if an minus 1 equals 0, and otherwise, I'm doing the swapping here, we have the unsigned value of these bits added to the negative value of 2 exponent n minus 1, and this minus 1 is in the exponent. And then the range of values that we can represent is from -2 and in the exponent n minus 1 up to 2 and in the exponent n minus 1, 1 less. So now about formalizing the rules for indicating an overflow. Basically what you saw in this picture, if we crossed this line, this red line, then it meant that, for example, we were adding 2 negative numbers and the result was non-negative. Or the other case would be that 2 non-negative numbers were added and the result was negative. In this notation where I show the mapping from bit patterns to signed values, I should take care of this name conflict here. A bit unfortunate that I use S for the sum and also for signed, but to avoid it here I just say that the value that I associate with this bit pattern as a signed integer is now called as tilde. So we would have an overflow if A is negative and B is negative, and the result, the computed result, is non-negative. Or, so this would be one case, or if A was non-negative and B was non-negative and the result was negative. And this logical expression is equivalent to A circled plus b, which is s tilde, is unequal to a plus b. So that means what we see in the bit pattern here as a signed integer is not what we would get if we do the computation with actual integers. Or in other words, this indicates a signed overflow. And now, of course, for indicating the signed overflow, we just have to realize this in Circuitverse. For that, we use the fact that we just have to check whether the signs are indicating a negative signed value or a non-negative signed value. So kind of easy to do that. Exercise for you is figuring out a way to indicate a signed overflow when we do a subtraction. And that means indicate a way to see whether this a circled minus b, which would give us a s tilde, is unequal to a minus b. But you might guess you can do it in a very similar way. So now let's go to Circuitverse. I already prepared a few things in Circuitverse, some input devices and some output devices, so that we can visualize the operations done by the adder. Here I will actually not use our adder, I will use the adder from Circuitverse, which you can find here. And it's just simplifying things. It's doing the same thing. You also have here A and B as the operands. You have some C in. You have here the computed bit pattern of the sum, and you have this C out. So it's just making it a bit more convenient here. So I just have to connect things, and that's it. Now, first of all, make yourself clear that the hex displays are just a convenient way to represent these bit patterns here. And how we interpret these bit patterns as either unsigned or signed values is up to us. We could read this operation carried out here as the unsigned value 4 plus the unsigned value 4 equals the unsigned value 8. In this case, we don't have an overflow, and we see this from this carry flag. Or we could interpret the computation as being signed 4 plus signed 4 equals minus 8, because this is the bit pattern that we identify with the signed value minus 8. And in this case, we should have an overflow. Another example, for example, this computation could be unsigned 15 plus unsigned 1 equals unsigned 0 in this unsigned interpretation. Or it could be signed minus 1 plus signed 1 equals 0. In this case, the unsigned interpretation would have an overflow, and the signed interpretation should not have an overflow. And now you can also play around with some examples that you, on the one hand, visualize with this picture, with this circle, and then also confirm the results with Circuitverse. Now, for building this device for indicating signed overflow, I will use two subcircuits. The first subcircuit just gives me the sign of a 4-bit input device. So this is A, and I have one output device. So this is called the sign, and in between I just need a splitter. I split 4 bits into 3 and 1. And this most significant bit gives me the sign. That means if I change here the bit, it flips, and these bits are just ignored. Now the next subcircuit actually computes this overflow, and the convention for indicating a signed overflow would be to set a so-called overflow flag, OF, and the convention for the unsigned overflow would be this carry flag, CF. So for that I have two inputs, A and B. actually 3 inputs, of course. And here I'm not using this tilde for the S. Just call this S. And then I have to pick up the signs of A, B, and S. So I need this subcircuit. Actually, I could have done this a bit nicer. Here, edit layout. Put this up, decrease the height, save it. No. Can do this nicer. Okay, now an overflow we have in case we need an AND gate if A is negative and B is negative and this S is non-negative. So I also need here a NOT. And the other case would be that A and B is not negative, so I'm just using here 2 NOTs. You can think about how to use fewer logic gates by rewriting the rules, but I want to keep it as simple as possible. So if A and B is not negative, no, and S is negative, we have the second possible case for an overflow, and if one of them is actually true or happened, then we have an overflow in total. So this would give us this overflow flag. Now we can check negative and negative, and result is non-negative, would indicate an overflow. And the other cases where we have non-negative A and B and negative S also indicates an overflow. And now this can be used in this main circuit here. I will just put this above. And then I connect this with A. And B with here, and now S with this one, and then I need an output for the signed overflow, and by convention that's called OF, indicates signed overflow. Now let's see, we have here some negative value with some non-negative value. The result is non-negative, no overflow. If we change that, for example here, we would have an overflow. And now again, go back to this picture with the circle. Make clear that you understand this mapping of bit patterns to either signed or unsigned integers, and check this result. Now the task for you is to find a way to do a subtraction. I mean, basically we already solved that problem, but then also indicate an overflow when we do the subtraction, and where we have to change a bit the rules behind this building block or add something to this building block. But I'm sure you know how to do that.